Did you know that a mobile phone has 100 billion switches on a chip the size of your fingernail? Have you ever wondered why laptops keep getting faster and cheaper? Whether you're a techno wizard or you don't know a terabyte from a terapin, join me in the race to build the ultimate computer.
Good evening and welcome to the Royal Institution. All around the world, scientists and engineers are locked in a fierce competition. The outcome will decide the future of mobile phones, laptops, games consoles, hundreds of other digital devices. It's a race to build the ultimate computer, and at its heart is the need for speed. Everyone wants to build faster computers. Now, computers have not been around for very long, but we can see just how much they've evolved already by looking at the world of computer games. Here's an example of a modern computer game, and you can see the very realistic graphics, something we've all become used to. But if we go back just 30 years, things looked very different. This is a classic computer game from 1978. It's called Space Invaders. And on the screen here, you can see a little clip of Space Invaders. And you see the graphics are very primitive, they're all two-dimensional, very slow. And in fact, they're all in black and white. And so the manufacturers of the console, and if we can just bring the camera in and take a look at this, they put strips of coloured plastic over the screen to try to make it look like it was a colour display. Then in 1981, we had the BBC Micro. And here we can see a game running on the BBC Micro called Elite. Now, the improved processing power of this computer allowed it to have a very primitive form of three-dimensional graphics. This is called wireframe. Then in 1994, we had this, the first PlayStation. And we can see it here running a game called Gran Turismo. This is a racing game. And because of the increased processing power of this console, we actually have solid three-dimensional objects. And the movement of the cars is based on physics. However, the landscape appears rather flat and unrealistic because the processor is not fast enough to imitate real-world depth and light. And then finally, here's a modern games console, and here we see it running a game called Fable 2. The graphics are now much more realistic, fully three-dimensional. We see reflections and shadows, all rendered in real time at high resolution. Now, the dramatic improvement in the graphics over the 30-year period since Space Invaders is a direct result of the huge growth in the processing speed of computers. While Space Invaders could do 500,000 instructions per second, a PlayStation 3, or this Xbox 360, can do over 300 billion. And it's not just games consoles that have been getting faster. Computers generally have been doubling in speed every 2 years. And this has been happening for the last 50 years. Now, when something doubles in a fixed time interval, it leads to a very dramatic kind of growth. We call it exponential growth. It's the way, for example, that populations grow. So here we see a population of bacteria. Now, every 20 minutes, each bacterium splits in two. So the total number of bacteria doubles every 20 minutes. And we see it starts off rather slowly, and then it takes off in this very dramatic way. Now, we can see for ourselves what exponential growth looks like by doing a little experiment. So if we can bring one of the handheld cameras in, we can have a look at this. So in this box, I have 225 armed mousetraps. And on each mousetrap, we have a ping pong ball. Now, in a moment, we're going to take one more ping pong ball, and we're going to drop it in through this hole in the top. And it's going to set off a chain reaction. And in this chain reaction, the number of ping pong balls flying through the air is going to grow exponentially. Okay, so who would like to volunteer to come and set this off? My goodness. Let's have you there. Yep. Yes, you'd like to make your way along the end of the road. if you'd like to come and stand just there, and just turn that way. Okay, that's good. And what's your name?
Matthew.
Matthew, you'd like to hold that. Now, in a moment, we're going to give you a 3, 2, 1 countdown, okay? When we get to go, all I want you to do is to place the ball in through that little hole at the top. You manage that? Yeah?
Yep. Okay.
Are we ready? 3, 2, 1, go! Amazing, excellent. Okay, thank you very much. Okay, so we have a high-speed camera that was looking at that, and perhaps we can just do a little action replay and see that in slow motion. So there's the first ball, setting off a couple more. Each of those is setting off several more. And on that curve, we can see the number of balls growing in this very dramatic way. And what's really impressive about exponential growth is that the rate of growth is itself growing exponentially. Now, the exponential growth of computer power is truly staggering. It means, for example, that the computers that will be made in the next 2 years have as much processing power as all the computers ever made, from the very first computer up to the present day. If cars had improved at the same rate as personal computers, then a typical family car today would travel 43,000 times faster than a Formula 1 racing car. And it would go 200 times around the world on 1 litre of petrol. Now, that amazing improvement in speed is made possible because of this. This is a microprocessor. And this is the microprocessor in its packaging. What we see here are gold contacts which connect the microprocessor to the rest of the computer. And on the other side is the processing chip itself. Now, to me, this is one of the most remarkable pieces of engineering ever created. On this chip, there are over 400 million components, and tiny chips like this have changed the world. We can see here a photograph of the surface of this chip. This has been magnified 100 times, and it's showing just a fraction of the incredible complexity of the circuitry. Now, as well as being very complex, processors are also very fast. For instance, they're very good at doing arithmetic. So let's just see how good you are at doing arithmetic. Okay, I'm going to bring up some arithmetical questions, and as soon as you know the answer, I want you to shout it out as loudly as you can. Okay, here comes the first one.
12.
Okay, excellent. Next one.
63.
Excellent. Next one. Okay, not quite so easy. Well, a microprocessor like this can do a calculation like that and get the right answer in a nanosecond. That's a billionth of a second. Now, that sounds very fast, but just how long is a nanosecond? Well, to find out, please welcome Hamish McLeod. Hamish. Hamish, welcome to the Christmas lectures. Now, you're a licensed firearms expert,
yes.
And you've brought a powerful-looking gun with you. Can you tell us something about that?
Yes. This is a .22 air rifle. It's probably one of the most powerful air rifles that's available on the market today. And certainly this gun would shoot a lead pellet just about as fast as any air rifle could.
Okay, impressive. What we're going to do then is we're going to time the pellet from this gun. Now, to help us do that, we've got some special apparatus over here. In a moment, we're going to mount the gun in this stand, and then we're going to fire it at this target. Now, if we look here, what we see is that the target consists of a circuit board, and on the circuit board, we've etched a pattern, a zigzag pattern of copper wire. So when the pellet from the gun passes through this circuit board, it will break an electrical circuit. Now, about 30 centimetres back, we have a second target with the same pattern of copper wire, and that's also connected to the same circuit. So the circuit will tell us the time from the pellet passing through the first board to the pellet passing through the second board. And the answer will appear on this laptop. So, Hamish, if you're all ready to load up.
Certainly.
Okay. And once Hamish is all set, we'll give him a 3, 2, 1 countdown, okay? Are we ready? Everybody? Yes. Okay. 3, 2, 1, go! Whoa! Okay, well that looked pretty much instantaneous to me, but apparently it took just over 2 million nanoseconds, that's 2/1000ths of a second, for that pellet to travel 30 centimetres. So in that time, our microprocessor could have done just over 2 million complex arithmetical calculations. Okay, Hamish, thank you very much indeed for joining us. So computers are extremely fast, and they're getting faster every year. And it's this amazing growth in power that's fueled the digital revolution. It's transformed the nature of entertainment, of communications, of healthcare. In fact, almost every aspect of our lives has been touched or even revolutionized by the microprocessor. And this is just the beginning. If microprocessors continue to improve in power, their impact could be far greater still. But a couple of years ago, we hit a big problem, which threatens to stop further growth in the speed of microprocessors. Now, to understand what the problem is and what we're going to do about it, please join me after the break. So let's look at why we might be reaching a speed limit for microprocessors. Now, to do this, we need to understand something about how microprocessors are made and how they work. And for this, I'm going to need a volunteer. Let's have you. Yes, you'd like to come on down. Okay. If you'd like to stand just there. What's your name?
Joe.
Joe. Okay. So a microprocessor is really a big electrical circuit with hundreds of millions of tiny switches. And to understand what they're all doing, we've got a simple example. So what we're going to do here is we're going to make a milkshake. And if we succeed, this light will come on. Now, to make a milkshake, obviously we need milk. So what I'd like you to do is to close this switch by moving that lever down. Okay? Now, the light hasn't come on, so obviously we don't have enough ingredients yet. So let's suppose we also have some strawberries. So would you like to close that switch? Okay, and the light comes on. So if we have milk and strawberries, we can make a strawberry milkshake. Okay, let's suppose we don't have any strawberries. Can you open that switch for me? And let's say instead we have some bananas. So if you'd like to close that switch. So again, if we have milk and we have bananas, we can make banana milkshake. Okay, let's suppose we have strawberries and bananas. So if you want to close that switch again, and the light stays on, of course. So what this says is that to make a milkshake, we need milk and we need either strawberries or bananas or both. Now that kind of reasoning is called logic, and computers are very good at it. Now the logic circuits in a microprocessor are vastly more complex than this, but the principle is just the same. They're based on switches which are either on or off. Okay, thank you very much. Now obviously, mechanical switches such as those are much too slow. We need a way to make fast electronic switches. And the key to this is a remarkable substance called a semiconductor. Now a semiconductor is something that's part way between a conductor, like copper, which allows electricity to flow very easily, and an insulator, such as plastic, which doesn't allow electricity to flow at all. And it's that in-between property of semiconductors which allows them to be switched very quickly between being an insulator or a conductor and back again. Now, in fact, the very first semiconductor was discovered here in the Royal Institution by Michael Faraday back in 1833. He was experimenting with a material called silver sulfide. This is actually quite a familiar material. I have here a silver tankard. As you can see, it's all nice and shiny. But if we leave this lying around for a few months, it becomes covered in this black tarnish. And that black tarnish is silver sulfide. Now, Faraday discovered that silver sulfide is a semiconductor. And in his notebook, he described this discovery as very extraordinary. But of course, he had no idea of the huge practical impact this discovery would have over 100 years later. Now, in time, other semiconductors were discovered, such as germanium and silicon. But the big breakthrough came in 1947 with the invention of this. This is called a transistor. And we can think of this as a very fast electronic switch having no moving parts. But how does a transistor work? Well, to find out, let's see how we can make a switch using water. So here I have a tank containing water, and we're just going to build up a little bit of pressure in this tank. So the water's now under pressure, and it would like to flow up this tube, along this tube at the top, through this valve, but this valve is closed at the moment, and then down into this collection container. Now what I'm going to do is to allow some of the high pressure water to flow into this cylinder, and it will move the piston and then open the valve. So let's see that happen. So this is now flowing into the cylinder, pushing on the piston, opening the valve, and we can see water flowing into the container. And if I turn the tap back and release the pressure in the cylinder, the valve closes again and the flow of water stops. So we've used water pressure to control the flow of water. Now, water pressure is a bit like voltage in an electrical circuit, and the flow of water is a bit like electrical current. So in a transistor, we use a voltage to switch on and off an electrical current. Of course, real transistors are much faster than this. A real transistor can switch in the time it takes light to travel just a few millimeters. Now here we have a model, a cross-section model of a transistor, and this has been magnified 10 million times. So on the scale of this transistor, the whole processor would be the size of Greater London. Okay, so how does this work? Well, this is the silicon layer at the bottom here, and on the top we have 3 copper electrodes. Now this electrode is connected directly to the silicon, and so electricity can flow in through this electrode, through the silicon, and then out through this electrode. This is a layer of insulation, and on top we have a 3rd electrode. Now, by applying a voltage to this middle electrode, we can switch the silicon between being a conductor, in which case electricity can flow from here across to here, or being an insulator, in which case no electricity flows. The insulation is important because it stops electrical current from flowing out of this middle electrode. And in a modern microprocessor, that insulation layer is just 4 atoms in thickness. Now, at first, transistors were packaged individually. And I have here a circuit board from a computer that was built in the early 1960s. And you can see each of these silver cans is one separate transistor. Thank you. Now, the next important development was called the integrated circuit. And here we can see an example of an early integrated circuit in which 4 transistors have been manufactured on the same piece of silicon. Now, in time, people made integrated circuits with more and more transistors on that same piece of silicon. First 10, then 20, and so on. And that was done by making the transistors smaller and smaller. Now, Gordon Moore, who founded Intel, noticed that the number of transistors on a chip seemed to be doubling every 2 years. And that's become known as Moore's law. And that's continued to hold for the last 40 years. The next generation of processor will have several billion transistors on each chip. Now, microprocessors are manufactured on the surface of a thin wafer of silicon, and I have one of them here. I hope you can see this. Each of those little squares is a single microprocessor of the kind that we saw earlier. Now, to me, it seems incredible that something which is so tiny and so complex can be made at all. It sounds almost impossible. Well, to see how it's done, we're going to have a go at doing something else which also sounds impossible. And for this, I'd like a volunteer. Should we have someone from this side? Yeah, how about you? Would you like to come on down? Let's just turn that. Just come and stand here. That's good. What's your name?
Briley.
Briley. Okay. What's your initials? What are your initials?
BG.
BG, all right. I'm going to give you a big marker pen. There we go. And I have here some rice, just ordinary rice. I'm going to take a little grain of rice. And I'm wondering, do you think you could write your initials on the side of that grain of rice using that marker pen?
Probably not.
Probably not. No, I think probably not either. Okay. Tell you what, to make it a little bit easier, we're going to do something different. Just wait there a minute. What I have here is just a sheet of plastic. What I'd like you to do is to write your initials, nice big writing, nice big fat writing, across the middle of that plastic for me. Okay? Excellent. Okay, that's good. Do you want to just go over that one more time? Make it really nice and big and fat. That's it. Lots and lots of ink is really good for this. Excellent. Wonderful. Okay, that's brilliant. Okay, let's just pop the top back on there. Now, what we're going to do with this, if you'd like to come with me, come over here. If you'd like to stand just there, we're going to take this and I'm going to pop it in this frame like this, and I'm going to switch on this light box. So this is just a box with a bright light inside. So lots of light is coming out, it's passing through your initials and spreading out in all directions. And over here we have a lens, and the lens is collecting some of that light and focusing it down onto this grain of rice. And we also have a camera which is looking at that little grain of rice as well. And if we can now take the feed, if we can take the feed from that camera and bring it up on the screen, if I keep out of the way of the light, we should just there, we can see, there are your initials written on a grain of rice. Okay? Okay, I'd like to do one more thing. Hold out your hand like this and put it in front of your initials, in front of the light box, that's it. And then hold it flat like that in front of the light box, that's it. And now just move it gently about, and we can see an image of your hand. Okay. Okay, thank you very much indeed. So to make a microprocessor, we can lay out the design of the processor on a large scale and then use a projection technique just like this to shrink it down to a very small scale. So we've seen how to project an image down to a small size, but how can we use this to make a microprocessor? Well, here I have a piece of a microprocessor that's partway through being manufactured. In fact, it's just the transistor that we saw earlier. And we're going to see how to lay down, how to create those 3 copper electrodes. And to help us do this, we have 2 workers from the microprocessor factory. Okay, and we'll find out in a minute why they're dressed in these strange costumes. So how are we going to make this microprocessor? Well, at the bottom here, we have the layer of silicon. And we've already put down the insulation layer. And the next stage is to lay down a complete layer of copper across the whole surface of the wafer. And then on top of the copper, we put down another layer of special material that's sensitive to light. The next thing we then do is to project an image of the copper wiring onto the top surface. So if you can bring on the light, please. So this pattern of light is the pattern of copper that we want to create on the surface of the wafer. Now the light is causing a chemical change in the material in this top layer. Okay, we can switch the light off now, please. And the next stage is to wash the wafer in a special chemical that dissolves away this green layer. But it only dissolves the material that wasn't exposed to light. So if we can just remove these 2 pieces now, please. Excellent. Okay, so the next stage is to wash the wafer in acid. Now, acid dissolves copper, but it only dissolves the copper where the copper is exposed. The copper that's underneath these green regions is protected. So let's add our acid and remove those 2 pieces then, please. Good. And now the final stage is to use yet another chemical to remove all the remaining green layer. So if you'd like to remove those 2 pieces, and I'll give you a hand with this middle piece. Okay, so now we've created our pattern of copper wiring. And if we just bring that light back on for a moment, we can see that the pattern of copper corresponds exactly to the pattern of light. And we can do this for the hundreds of millions of transistors on the microprocessor all at the same time. Now, all of this has to be done under incredibly clean conditions. In fact, it's 10,000 times cleaner than an operating theatre. Now, to see why, imagine that just one speck of dust got into the optical projection system. We'd get an image of the speck of dust. Now, on the scale of this transistor, a speck of dust is 100 meters across. So if we get an image of a speck of dust instead of an image of the wiring, we've ruined the circuit. And that's why Alex here and Elaine are dressed in these rather strange-looking suits. They're called bunny suits. Is it hot in there?
Boiling.
It looks really hot. So these suits are not there to protect the workers. They're there to protect the microprocessor from any dust which they might bring with them into the factory. OK, we'll say thank you to our volunteers and join me again after the break. So we've seen that microprocessors are made of millions of switches called transistors. And we've seen how to make a microprocessor by projecting light. I now want to explain something very extraordinary about this way of making microprocessors. The cost of making a wafer, such as this, doesn't really depend very much on the exact details of what we make on the surface of it. In particular, if we make all the transistors half the size, then we can fit 4 times as many transistors onto the wafer, and so we can fit 4 times as many processors. And that means each processor is now only a quarter of the cost. Now, usually in life, things which are cheaper are not as good as expensive things. But in the case of microprocessors, something amazing happens. When we make the transistors smaller, they actually become faster. If we think back to that water model earlier, if we made it smaller, the cylinder could fill up with water more quickly. And the same is true of transistors. A smaller transistor can fill up with electrical charge more quickly. Now, faster transistors means the computer is more powerful. The rate at which transistors switch on and off is called the clock speed. And if you've bought a computer recently, it might have a clock speed of, let's say, 3 gigahertz. That means the transistors are switching on and off 3,000 million times a second. So smaller transistors means they're faster, and it means they're cheaper. And also, having lots of transistors to play with allows the designers of the microprocessor to use more sophisticated circuits, and that also allows the processor to run faster. Now, this extraordinary result explains why it is that computers have improved in such a dramatic way over the last 50 years. But remember, I said that a couple of years ago we hit a big problem, which threatens to stop further growth in the speed of processors. Now, to see what that problem is, I'd like to try a little experiment, and I'd like you all to join in, please. I'd like you to imagine that each of you is a transistor in a microprocessor. Now, at the moment, you're all switched off, so you're all nice and relaxed and nice and cool. OK, what I'd like you to do, I'd like you all stand up, please. OK, now you're all transistors that are switched on, but you're not using too much energy, so you're still fairly cool. OK, I'd like you to sit down, please. And I'd like you to stand up again, please. OK, sit down. OK, can you all stand up, please? OK, you can all sit down now, thank you. OK, so by now you're probably feeling quite a bit hotter. Now imagine that we packed twice as many of you into the same space and asked you all to stand up and sit down again. Then you'd be generating twice as much heat, and we'd need more ventilation to keep you cool. Now imagine we also asked you to stand up and sit down twice as fast. Then you'd generate even more heat, and we'd need even more cooling. Well, it's just like this for the transistors in a microprocessor. When they're off, they don't use much energy, they don't produce much heat. When they're on, they also don't produce much heat. It's only when they're switching between on and off that they use energy and produce heat. Now, to see why it is that transistors only produce heat when they switch, let's look again at our water model. So this is just like the previous model that you saw. The only difference is that we've added a second valve here. Now, this valve is the opposite way round to the first one. So when the first one is closed or off, the second one is on or open. And when this one is off, the first one is on. So let's see what happens when we allow high pressure water into the cylinder. So as the piston switches on this valve, it allows water to flow through into the container. But in a moment or two, this second valve will close, and so the flow of water stops. Now, the flow of water, remember, is like the flow of electrical current. So what the designers of microprocessors do is they do a similar trick. They use transistors in pairs so that when one of them is on, there's another one which is off, and that stops current flowing. And the flow of current uses power, and that generates heat. So because the transistors only produce heat when they're actually switching, it means that modern microprocessors are very efficient in their use of energy. So making transistors smaller makes them faster, it makes them cheaper, but it also means they produce more heat per unit area. So although modern microprocessors are very efficient, as we approach 1 billion transistors on a chip, they're going to be producing a lot of heat. Now, to show you just how much heat, we did a little experiment. We took a standard personal computer, which you see on the right here, and then Ian and Nathan took it all apart and laid all the components out on a board. And over here, we see the end result. Here are the different parts of the computer laid out. This is the main circuit board of the computer. This is called the motherboard. This houses many of the important components. For example, along here we have the memory chips. And this is the power supply here. This is the hard disk. This stores all the data and the software. And the processor itself is on the motherboard. It's underneath here. And usually, on top of the processor, we have a piece of metal like this, which is called a heatsink. And on top of the heatsink, we have a little fan to keep it cool. Now, we've removed the heatsink, and we've replaced it with this copper dish. Now, this computer's been sitting here for a while, doing 1,000 million calculations a second. And so what I have here is an egg. I'm just going to crack the egg and put it into that copper dish. And we'll come back to that in just a moment and see how that's getting on. Meanwhile, let's just have a look at a little photograph of a computer circuit board. And this photograph has been taken with a special camera called a thermal imaging camera. And so the different colours here represent different temperatures. So the purples and the blues, those are low temperatures, and the yellows and reds are hotter temperatures. The white is the hottest of all. What we can see is that the hottest part of the computer is actually the microprocessor. Okay, let's have a look and see how our egg's getting on. And it's actually cooking very nicely. In fact, I think my supper will be ready by the end of the lecture. Okay. Now, really, that's just a bit of fun. But in fact, heat has become one of the biggest problems that microprocessor designers have to face today. In fact, a microprocessor today is producing the same heat density as the hot plate on a cooker. If we just continue to double the speed of processors every 2 years, then in 10 years' time, the heat density on a microprocessor will be the same as the heat density at the surface of the sun. Now, unless that heat can be taken away quickly, the processor will overheat and fail. So heat has become the main factor which limits the speed of modern microprocessors. So how are we going to solve this problem? Well, instead of just switching the transistors on and off even faster, manufacturers are trying a different approach. A couple of years ago, they started putting 2 computing engines called cores on the same chip. And we have here the photograph that we've seen earlier, and you may have noticed that this part of the processor looks a lot like this part. In fact, this is just a copy of this part. These are actually 2 separate processing cores on the same piece of silicon. Now, with 2 cores running at the same speed, that processor should be twice as fast. And we call this parallel processing. There's a little snag, however. Not all tasks can be shared. For example, it takes a woman 9 months to make a baby, but 9 women can't make a baby in 1 month. Now, fortunately, many important computational problems can be shared efficiently across many cores. So over the next few years, we'll see processors with 4 cores, 8 cores, 16 cores, and so on. And this will allow the speed of processors to continue to double every 2 years for at least some time to come. But is there a way to build vastly more powerful computers? Well, here's one idea. This is a model of what's called a carbon nanotube. Each of these is a carbon atom. Now, if we can build a transistor out of carbon nanotubes, it could switch 1,000 times faster than a transistor made of silicon. Now, here's an even more exotic idea. What about using DNA to store information and to process it? A computer made of DNA could be 10 billion times more energy efficient than a computer made out of silicon. And the DNA in one human body can store 10,000 times as much data as all the personal computers in the world put together. Now, it's unlikely that general-purpose computers will ever be made out of DNA, but one day we might be able to build intelligent drugs that use DNA computation to detect, for example, when a cell is about to become cancerous and to take the appropriate action. Now, it might be many decades before ideas such as these become reality. But in tomorrow's lecture, we'll look at some of the amazing new technologies that are already changing the way in which humans and computers interact with each other. Join me then. Thank you.